do this thing, guys. This may be another short and sweet one. Okay, today we are going to be all about measuring temperature. A bunch of you guys have thermal systems for capstone, and this is going to be really important to see how your performance is doing. On a side note, I got through all of the initial paragraphs that you guys turned in. In general, they were good. A few of them got a little bit wordy, but okay, whatever. I think when I do it next time, what I'm going to do is I'll ask the students, just write me one sentence to start off with. To say, what do you want to investigate? And say, like, I want to investigate the power output from my wood stove thermal collection system, and I'm going to measure the power output and the H value of the radiator system. Okay. I think that would have made things a little more focused, a little more directed. When we do the class evaluations, you guys can tell me what you think. Or just stop by my office. Door's always open. Okay, measuring temperature. So we could just grab our handy-dandy alcohol thermometer and read the temperature off it due to the expansion of alcohol in a closed volume. That's great. But when you get to automated systems and measurement, not so helpful. So let's go to the next oldest system, which is thermocouples. Okay, thermocouples, they're a pair of dissimilar metals in electrical contact. They can be twisted, soldered, or welded. And that's what I have going on over here. So I've got a J-type thermocouple. I twisted both ends, and I cut it right in the middle. So the two conductors go in this black sheet, and I'm going to measure the potential across the red wire that I cut into. Okay. So the sum of the gradients results in an output voltage. However, in order to read the actual temperature, we need to have a reference. So in the case of the J-type thermocouple, it's fairly linear, and you get about 50 microvolts per degree C. Okay, but, okay, that gives me the slope of a line, but where is that line on a temperature voltage chart? What we do is we define 0C as 0 volts. Why 0C? It's easy. Okay? These things were around in the 1860s when this was state of the art. And if you just put a bucket of ice water at one end, you're at atmospheric pressure, and that's well stirred, okay, you know you are at 0C right up until the point that all the ice melts. So let's do it. I have a bag of ice. Put that in our little beaker and on the floor. Tap water, make sure I get good thermal connection. No, we're not making a vodka martini. I'm showing about 0.86 millivolts. Okay, not a ton of voltage. It's another one of those small signal kind of measurement deals. So what we can do is we can now go to the J-type thermocouple tables and we can look up the voltage. So here's the J-type thermocouples, and you'll notice we have 0 volts at 0C. And all we have to do is read over to get the voltage. So 0.93. So let's see. So this would be 0 volts, 1 volt, 0C, 1C, 2C. And it comes all the way over to 10. So this is 10C. And that just happens to match the start of the next column. So if we are at 0.96, that says that we are at 19C in this room. Okay? Not too bad. And this actually is, I took this from the PE exam. So that's great. We got our bucket of ice water, we got our voltage, we know the temperature from the tables, but I really don't think that, you know, if you're at National Instruments or something like that, you want to tell the customer that they got to have a bucket of ice water to go get a temperature measurement. That's rather inconvenient. So what we do today is we have something called ice point reference chips. So we take just one twisted pair and we bring it back to the reader chip, and then that outputs either an analog voltage or an I2C command, something like that, that we can then read electronically. So one of the devices that you can use is the analog devices AD594. And all this is doing is taking the place of a bucket of ice water. And it's amping up that little tiny signal so that it's something readable. Okay, for those of you that want to use thermocouples in your 443 project, this is what I have for you. Okay. I have the okay, so I have this little Adafruit breakout board. You must have this. Okay, you cannot just go read a thermocouple directly with an Arduino's analog input. Won't work. You need this as an amp and an ice point reference. And I just happen to have one. You'll notice that, there we go. I've got my thermocouple, and I've got all of my connections for I2C. So I've got power and ground, and then these are all my data lines coming back. And it really is kind of a snazzy little chip. You can hook up multiple of them. You can do software I2C ports. already got the code loaded up in this Arduino, so it should be sending back information. Let's try it again. PID. You'll see that other one soon enough. So the programming is a little bit more involved, folks. As you can see, it's not bad, and I've posted that chunk of code. And if I put my fingers over the thermocouple, yes, in fact, it does prove that I am alive and I am a warm-blooded creature. Okay, so thermocouples, very nice, but you got to use an ice point reference if you want to play with them. And also, you got to understand their limitations. Okay, here's the curves for the various types. There's all kinds of different metals. Definitely want to choose the metal that's best for the temperature range that you're using. J and K are very common. I see those all over the place. Some of the others, yeah, you know, they're better for high or low temperatures. In general, thermocouples are not as accurate as the next class of temperature measurement we're going to talk about, which are thermistors. If you need resolutions below 1C, thermocouples are generally not going to get you there. You've got to use something else. Okay. So always check the manufacturer's data sheet. Here's your use ranges. And these are great, but I want to caution you on something. Okay. This little thermocouple right here. Okay. No, you guys can see that. Maybe not. Okay. This little piece of wire, all this coating, that's just a simple plastic coating. So if I were to take a J-type thermocouple up to, like, 1300 F, that coating is going to go away. So even though your metal may handle the temperature, make sure your coating is going to handle it. There's all kinds of cool ceramic coatings, things like Nextel that are woven ceramics. Those are great. Always watch your insulation as well as your metal type. Okay, so they are low to medium cost. They got a wide temperature range, and that's the beauty of these things. So what I like to say to people is, if you're dealing with any kind of a normal temperature, by normal I mean between dry ice and boiling water, okay, go to a thermistor. They're cheaper, they're easier to deal with, you don't need an ice point reference. If you're outside of that, if you're going to be up in the organic chemistry range, or you're measuring a flame temperature or something like that, yeah, that's the thermocouple world. Okay, thermistors. Let's move on to the next class. I mean, there's not a lot else to tell you about thermocouples. Thermistors. You probably played with these in the 370 controls kits. It is just a temperature-sensitive resistor. That's all it is. And they can either increase or decrease resistance with temperature. The relationship is absolutely not linear, folks. Okay, for thermistors, your temperature resistance relationship is going to be some variation of that. Okay, the Hard-Steinhardt equation. And remember, your T on this, absolute degrees. It's not C or F. And A, B, and C are your device-specific coefficients. So where do you get all that? All right. Let's take a look at one. This is a thermistor that I keep in Crosby. I love this little thing. It's not very expensive. It's got a good temperature range. It's got that nice little mounting lug so you can put a number 2 screw down through it, hold it in place. The little ring lug gives you really nice thermal contact. Nice little device. So if you want to go find this, let's go to the data sheet for this device. Not a robot, just take me over. It is such a secure website, you can't use it. All right. If I can do it this way. Really, guys? That part number is okay, so here's the actual part that I stock in Crosby. For pretty much all the stuff you guys are doing, I would recommend going with this. Some of you guys said you wanted to use thermocouples. That's up to you. If you want to fight that demon, go for it. But you're going to find this is a whole lot easier. So we'll go to the data sheet. Here's the data sheet with all the specs on it, max use temperatures, all that good stuff. This thing is 10,000 ohms at standard room temperature. So if you put it in a voltage divider with a 10K resistor, you're going to have a nice little temperature measuring device. And to get those Hart-Steinhardt equations, we can go to the NTC curve computation. I will put in the part number. I'll say export. And it will generate this. Okay, so here is the resistance table right here. So here's your resistance at minus 55C all the way up to 125C. That's not bad. That's a pretty good temperature range for a device that costs $1.78 in single piece quantities. So right here we have RT. This is resistance as a function of temperature, that ugly little equation. And below, we have temperature as a function of resistance. This is actually that Hart-Steinhardt equation, and they decided to convert it to Celsius. Okay, whatever. I was overly nice to you guys. Because what I did is I actually put all that information in this lesson folder for today. And if you look in this thermistor reading demo, I put all the equations right in there as an example, so you don't have to fight with those. Sometimes Arduino's math abilities leave a little bit to be desired. So you will find all of that in there. So here's an actual implementation of the thing. And I made a little shield because I hate protoboards. Okay, they're too loose, they're too noisy. And this thing, if you can see it, is the teeny tiny little thermistor. So let's try this one. Now there is no fancy circuitry in this thing. The only thing I've done on this shield so the shield is nothing more than, it's 3 voltage dividers. So I took 5 volts, I went across the thermistor to a 10K resistor down to ground, and I took the output of the voltage divider, took it to A0, 1, 2, 0, 1, and 2. Yes?
Could you look up more than one thermistor?
Absolutely. You can put as many as you want.
Get the readings from all of them?
Absolutely. Yep. Yeah, this is specifically a 3-channel. But I could have made it for every single analog input, and it would have run just fine. Okay, so I went to from the data sheet, I pulled out the Hart-Steinhardt coefficients, ABCD. I read the analog input, and we'll do bits, and, well, let's just run this thing. And this one is 600. And there you go. So we go from bits, just reading the voltage divider, and then I converted that to volts, and I converted that to resistance. So it's a little bit higher than typical room temperature resistance. Then I took it to, let's see, took it to Kelvin, Celsius, and Fahrenheit. And 68 Fahrenheit, that is actually, now, this is saying 65. But okay, I could buy that. So, thermistor, much easier to implement, folks. And here is that page from the data sheet. Here's the RT curve. So you can see highly nonlinear. It's not like the thermocouples at all. Now the nice thing about thermistors, much more accurate than thermocouples. So you can get quarter-degree C increments pretty easily with thermistors. You're just not going to get that with thermocouples. So you're trading accuracy for a measurement range. Use the appropriate tool. And they can be really cheap. So that little bitty thing, that's a thermistor that's 3 cents in quantity. You can also get them mounted in NPG pipe fittings like this. A little more expensive at $25 a pop, but it's a really nice sensor. So all kinds of good stuff. Okay, if you need really high accuracy, or you need really high stability, okay, this is where RTDs come in, folks. To be honest with you, I have never used one. So I'm really not the best at this, okay? They are just really accurate, really expensive, but if you need the accuracy, money talks. So you can do plus or minus 0.3 degrees C at 0 C. The class AA's are 0.1 degrees. You know, if you're in a research environment, maybe you need that. In a typical manufacturing or process control, no, you generally don't. Okay. So they're like thermistors in that they change resistance with temperature. But they can take much greater changes in temperature without damage. A lot of them are made of platinum. Those are the ones that I've had minimal experience with. There's also copper, nickel, wrapped around a glass or ceramic core. And they're typically 100 ohm plus or minus 0.1 ohm. Blah, blah, blah. So good for long-term stability. They're not going to wander much on you. And this one from Omega, $32 a pop. Okay, this is a little more fun. What if you want to measure the temperature of some HIV or some Ebola or starch corona? That's where things get a little more interesting. And that's where your non-contact stuff comes in. Everything above absolute zero gives off black body radiation. Hopefully you remember that from heat transfer. And the power coming off varies with the fourth power of temperature. So what we can do is we can take that radiation coming off, we can put it through a lens, we can shine it on a thermocouple, and we can use it as a measuring device. And generally what you're going to do is if you're going to shine that radiant energy onto a thermocouple, the signals are too small. So what you'll do is you'll put multiple thermocouples at the focal point of that lens and you'll make a thermal pile. And that's kind of what you got going on with these little things. These little infrared temperature thermometers. And they're nice. I think you got to be careful with these, folks. These are correlated to emissivity of 0.9 from the factory. They are not that accurate. I wouldn't trust this thing to like better than maybe 10 degrees either way. If I needed more than that, I'd go get a thermistor, thermocouple, and actually measure it. Okay, so you can also you can look at the spectral distribution. So as we go up in temperature, the frequency is going to get higher and higher and higher of the emitted light. And it goes according to this equation. So when you really want to measure something hot, you can see that peak is shifting in wavelength. And it's all shifting toward the shorter wavelengths, higher energy kind of stuff. I mean, that's 9,000 Fahrenheit. Okay, we've done measurements that high in Crosby only one time, and we were measuring ICBM rocket nozzles in compression. Unless you're doing that kind of stuff, you don't need this. Right? So yes, you can look at frequency and you can get temperature out of it, but it's pretty involved to do it actually correctly. All right, questions for me, folks? And as I promised, we have ended early. You are free to go. Get on your experiments, folks. Do not let